Okay, cool. Thank you. So welcome back to another session. Before we start, as usual, do you have any questions for me? Do you have any comments? Are you having troubles with anything? Okay, so once more, I encourage you to reach out, right? Try and see if you can schedule an appointment if you need time, right? If you need more practice on some examples, if you have any questions, feel free to reach out, right? Please don't wait. As you always know, it always comes quickly, and before you know it, you'll be taking our exam, right? So yeah, the earlier the better. Okay, anyways, let's continue from where we left off the last time, if there are no questions or comments. So last time, the last thing we were looking at was session 4.2, right, which was the mean value theorem. And I think we almost wrapped up everything, right? We were just left with one slide. So let me just go to my screen. I'm sharing my screen at the moment. Please, if you can't see, do let me know. I'm sharing the PowerPoint. Okay. So with the mean value theorem, right, we were able to see some ways where it can be applied. And especially, this is the first case that you see. Most of the questions are straightforward. You just have to make sure that the function satisfies the first two hypotheses, right? So the function is continuous on a closed interval a to b, and is differentiable on an open interval a to b. If those two conditions hold, then there is at least one c inside the a and b such that what? The slope of the tangent line at that c equal to the slope of the secant line joining the endpoints, right? So most of the time, they'll just ask you if it satisfies the hypothesis, and then they will ask you to find a C, right? Yeah, so most of the questions appear to be like this problem, the example 3 that we solved. But as I showed you the last time, we can also have other applications, right? Like this one, when we are trying to figure out a maximum possible value, and we have information about the derivative and then another function point, right? We can also use the mean value theorem to try and get an idea of how large something can be, right? Can possibly be. Okay, so we wrapped up this example. And then the last slide here goes as follows, and it's a theorem, right? The theorem says, now the mean value theorem here establishes one of the fundamental facts of differential calculus. Now, in a sense that what it's saying is, if the f prime of x is equal to 0, don't forget that this is the conclusion of the Rolle's theorem, right? The Rolle's theorem. If f prime of x is equal to 0 for all x in the interval, right, a to b, then that means that the function is constant on that interval. Now you can easily see this theorem, the application of this theorem, by going back to the first slide. The first set of examples, the graphs. Now looking at graph A, right? Just look at graph A. You can see that for graph A, we said that every c in the interval a to b, at every point in the interval a to b, right, there is a c, the c's are infinitely many, in a sense that at every c, the derivative or the slope of the tangent line will be equal to what? The slope of the what? Of the secant line joining the endpoints. And as you can see, this function is horizontal. It's a constant, right? So that theorem is just based on this first example. So what it's saying is, if your derivative is 0, right, on an interval, on a general interval, then that means that your original function is constant on that interval, right? So that's one of the fundamental theorems, right? So this is what this is saying. Now, a corollary is something that follows after a theorem, right? So the corollary is saying that because this is true, if f prime of s is equal to j prime of x, right? If two derivatives are equal within an interval, right, within an open interval a to b, then the f minus j is constant on a and b. Now, how come this is a corollary, right? How come it's a corollary? Now, let's see what this is saying. Now, for the corollary, right, for 7, when we say f prime of x equal to j prime of x, now what that implies is f prime of x, we can just say f prime of x minus j prime of x equal to 0. In other words, the derivative of a difference is the difference of the derivative. So this is the same as writing it as derivative of f of x minus g of x, right, equal to 0. Please, I hope you can see that. Do you have any questions on that? Okay, so if you can see that, then just consider this to be like a function, like say let me use a different color here. Let's say this f of x minus g of x, let's say it's h of x. If it's h of x, then it reduces to what we have here, the theorem, right? Because what we are saying is the derivative of h of x is 0, which is the same as the theorem we saw here. That's why there's a corollary. So what this is saying is, if the h prime of x is derivative is 0, then the h prime of x, then the h of x is a constant. So let's say c is the constant. But what is h of x? We decided to name this h of x. H of x is what? Is f of x minus g of x. So if h of x is equal to c, then what you're trying to say is f of x minus g of x is equal to c. So in that case, we can say f of x is equal to what? G of x plus c. So that's where the corollary is coming from, right? That's how come this is true, because it follows from the theorem. It follows from the theorem. If you just rearrange this to make it a difference of the derivative of a difference equal to 0, then that difference can stand as a single function whose derivative is 0. Hence, that difference will also be a constant, right? And then you can get f of x equal to g of x plus c. But you see a lot of this when we get to the later part of chapter 4, I think 4.9 or so, when we talk about antiderivative and stuff. Yeah, but please, that's the end of session 4.2. Do you have any questions on this? Okay, anybody needs time here? Okay, then let me close this. And then let's get to this. Okay, now I'm sharing a new PowerPoint slide, and this one is on 4.3, right? Now, 4.3 will be very key going on. I think on the exam, this one will be worth about 10 points. The content here will be worth about 10 points, right? Okay, so now in 4.3, we are just going to look at how the derivatives affect the shape of a graph, right? How the derivatives affect the shape of a graph. So we start with the first derivative. So what information does f prime give about f, right? Or what does f prime say about f? Now, to try and establish what the relationship between the f prime and f is, right? Let's look at this graph. The graph is in blue and its tangents are in, I think, red or pink or whatever. Yeah, the tangent lines are drawn on the blue line. Okay. Now, as you can see, from the point A to the point B, the blue function is increasing. From the point B to the point C, the blue function is decreasing. And then from C to D, the blue function is what? Is increasing, right? So it's increasing, decreasing, increasing. Okay. Now, from the point A to B, we know the function is increasing. Now, let's turn our attention to the derivative, right? How does the derivative appear to be from the point A to B? Well, as you can see, when we try and look at the slope of the tangent line, in other words, the derivative, right, across this point, then it's always positive. It's always standing up, right? It's like so. It's a positive slope. This is a positive slope, right? Now, on the other hand, okay, now let's look at the C to D, from C to D. From C to D to is increasing. Now, what is the behavior of the derivative as well on there, right? The slope of the tangent line is also going to be positive, right? Now, on the other hand, from B to C, where the function is decreasing, let's look at the derivative or the slope of the tangent line. Well, as you can see, the slope of the tangent line is what? It's like so. It's decreasing. It's always minus, right? It's decreasing. It's minus. The derivative is minus. It's a negative, right? Where the function is decreasing. The function is decreasing. The derivative is negative. So this leads to a very nice conclusion, which we call the ID test, right? The increasing or decreasing test, or short form is ID test, right? So what we've seen from the graph is where the function is increasing, its derivative is positive, and where the function is decreasing, its derivative is what? Is negative. You see, so that's the dynamic. So that means if you have the f prime and you want information about the f, then you can use you can get the information regarding the increasing or decreasing nature of the function, where it increases or where it decreases, using the first derivative, right? So the ID test is saying if the first derivative is what? Is positive on an interval, then the function is what? Is increasing on that interval, right? On the other hand, if the first derivative is negative on an interval, then the function is what? The original function f is decreasing on that interval. And that's just that. That's the increasing or decreasing test. So the first derivative gives us information about whether the function is what? Is increasing or decreasing. Please, any questions on this? Anybody needs time here? Okay. Now, let's try and apply this to a function. So how do you get the first derivative to test the intervals of increase or decrease? So to do that, we are looking at this example. So I'm going to do this on the PowerPoint, right? I'm going to do this on the PowerPoint since the solution is here. So let me go to the PowerPoint slide. This is example 1. I'm sharing the PowerPoint, no, not the PowerPoint, the whiteboard, sorry. I'm sharing the whiteboard now. If you can't see, do let me know. So example 1 on slides. Okay, so for this one, the function we are considering is f of x equal to 3x to the power 4 minus 4x cubed minus 12x squared plus 5. And you're interested in where it's increasing and where is what is decreasing. Okay, so let's walk through how you're going to do this. So solution. Okay, so to start this, as you know, for increasing or decreasing, we need the first derivative. We need the first derivative. So that's the first thing you have to obtain, right? So let's try and get the first derivative. Now this is a polynomial, right? So the derivative is just going to be, for this one, you're just going to be using constant multiple rule and then a power rule, right? So for the first part, we get what? 12s cubed. For the next part, we get 12s squared. And then for the next part, I get minus 24x. The derivative of 5 is 0, right? So that's the first derivative. Now, after getting this, after getting the first derivative, that's the first thing you do, right? Get a first derivative. Now, after getting this, you have to factor the first derivative, right? So we factor the first derivative. So let me factor this first derivative, right? So in factoring this, let's see, I can factor out 12 and I can factor out x, but then that will leave me with s squared minus x and then minus 2. Right. So with the x squared minus x minus 2, I can also still factor this, right? So I have 12x, and then for s squared minus 2, I'm just looking for two numbers whose product is -2 and whose sum is -1, right? So those two numbers are -2 and +1. So factorization complete. Now I'll try and explain the motivation for factoring the first derivative along the line, right? But this is it. Right, so we factor this. That's the next step. Sometimes your first derivative will be such that you can't factor. Like if you get a single quotient, that one you can't factor. So in that case, you just leave it like that. But if it appears like a polynomial or something else that you can factor, then you have to factor, right? Okay, so we are here. That's the next step. Now, after factoring, you try and find critical points, right? So find critical points or critical numbers using the f prime, right? So that's the next step. Now, from our previous lesson, we learned that to get a critical number, you need to check for two things. You need to check where the f prime of x, any x that will make it DNE, or where, or the second case is where the f prime of x is equal to 0, right? So where f prime of x is equal to 0. So two cases, okay. Now, in this case, for this polynomial, the original domain of f, right? The domain of f here is what? So the domain of f, that one should also be acknowledged. The domain is -infinity to infinity. So the domain is -infinity to infinity, right? So the question is, was there any x which was part of the domain, which is now making f prime undefined? That's the first case, right? The first condition, where f prime of x is equal to DN. Right? Is there any x which is making the f prime undefined, which was originally part of the domain f? Well, as you can see, the domain is all real numbers, and then for the f prime too, its domain is all real numbers. So there's no such x which will make the f prime DNE. So that means that this first condition will give us no critical points. Right, for this first condition. Now let's move on to the second condition. Now, for the second condition, we know we are supposed to set f prime of x equal to 0 and solve for x, right? So now, there's one motivation why we factor the f prime. Because you have it factored, when you are trying to solve for this equation, it becomes very, very easy, right? There's one motivation. But this is not even the most important motivation. I'll show you the most important motivation. It will come up down the line. But please, any questions so far? Okay. Now moving on, we have three factors being equal to 0. So that means that either 12x equal to 0, or s minus 2 equal to 0, or s plus 1 equal to 0, right? So with the first one, you get x equal to 0. And then for the second one, you get s equal to 2. And then with the third one, you get s equal to -1. So that means that since we didn't get any critical points for the first condition, and all the critical points we obtain here, we list them, right? So the critical numbers or critical points are, so those are 0, 2, and -1. We got them all from the second condition. Please, any questions so far? I hope you're okay. You understand up to this point. Okay. Anybody needs time here? Okay. Now, the next step is partition the domain of F, right? So I'll need to move on to the next slide. Once again, if you need more time, let me know. Okay. So the next step will be partition, right? Partition the domain of F using the critical numbers. Right? Now, sometimes some domains come already partitioned. So please note that, right? Some domains already come partitioned. Maybe the function may be undefined, so it will partition at those points. But the statement is partition the original domain. So if the domain is already partitioned, bring the same partition domain and then partition again with the critical points. Please, I hope that makes sense, right? So if the domain is already partitioned, don't ignore the partitions which are already there, right? So note the statement well. It says partition the original domain, the domain of F using the critical point. So in this case, in our example here, the domain of F is all real numbers, right? So it's from -infinity to infinity. So this is the original domain. So now let's partition this using the critical points. Now critical points are 0, 2, and -1. So -1 is the leftmost point. So you have -1, you have 0, and you have 2. So the partition I have here are this, 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 and this. So I have 4 intervals, right? Now, after getting your 4 intervals, you make this nice table here. So you need your intervals. You've created your intervals. Now, this point here, I'm going to illustrate why we factor the F prime. Now, for this one, we will have to, don't forget for the ID test, we just need the sign for F prime. We don't need the magnitude. For example, if you have -2, you only need the fact that it's negative. You don't need a 2. You don't need a 2 aspect, right? So the motivation is to get the sign. So what we know is F prime is this function. It's made up of 3 factors. Okay. So now all that I'm going to do is I'm going to create a table and then check the signs for these 3 factors, right? So the first factor is 12x. The next one is x minus 2. The next one is x plus 1. Now, I know that the product of these 3 will give me my F prime, right? Because F prime is the product of those 3, right? And then afterwards, I'll be able to get information about, I think I'll need more space here. So let me leave this for now. I'll be able to get information about f of x. Right. Okay, so now what are my intervals? Looking at the partition we created up here, the intervals are -infinity to -1, -1 to 0, 0 to 2, and then 2 to infinity. Okay, now all that we need is to just identify the sign, right? Just look at the interval and identify the sign of the expression in that interval, right? In that interval. Now, no matter the number you pick within any interval, please don't pick the endpoints, right? Don't pick the endpoints. As you can see, this is an open interval, right? Don't pick the endpoints. Now, you have to pick a number in between them, like in the interval, in between the endpoints. Now, no matter the number you pick, it will be the same conclusion. So it doesn't matter. So always pick a convenient number to deal with, right? Always pick a convenient number. Now, because you are not allowed calculators on your exam, that is why this is very important. The factoring part of the F prime is important. Now, let me show you a quick example here on the side, right? This is just an illustration. So let me say you have a function, right? Let me call it G of X so that it doesn't match this. I say you have, say, x squared minus x minus 2. Well, let me use something similar here. Minus 2, yeah. Minus 2. Let me use this similar thing. Now, the thing is, let's say I'm interested in the sign of this function. Or let me use J prime so that it matches or it tallies with what you're doing. Now, let's say I'm interested in whether J prime of x is positive or negative. So I have an interval, let's say negative infinity to negative 1. Let me pick a number. I'm picking the number, say, negative 2. Negative 2 is in this interval. Now, right away, if I want to check for the sign of negative 2, if this is not factored, then I'll have to plug in the negative 2 here and do, okay, negative 2 squared minus negative 2 and then minus 2. Now, what is this going to be? Negative 2 squared, oh, that's 4. And then minus 2, that's plus 2. And then minus 2, okay. And then what is this going to be? Okay, 4, 2, so that's 4. But the thing is, I don't need this 4. I just need the fact that this 4 is positive, right? So if I don't factor, I'll end up with a 4 and say, okay, I understand that J prime of x is what? Is positive on this interval. But this one is excess information. Now let's look at the second case where someone else factored this. So someone will say, okay, this J prime of x, which is x squared minus x minus 2, is the same as what? X minus 2, x plus 1, right? But then the person said, okay, I need the same interval, negative infinity to negative 1. I'm picking the same number, negative 2. Let me see if this one I can get the sign much quicker or in a much more convenient manner than the previous case, right? So J prime of s equal to 2, J prime of negative 2. Now, I just want to see if this is a positive or negative. Now, since it's factored, if you just test the negative, right, the negative 2 in here, you know that, oh, for negative 2 here, negative 2 minus 2 is negative, right? It's negative. It's a negative number. And negative 2 plus 1 is also a negative number. Negative times negative. I know this is positive. You see, this one is quicker and easier than plugging in the value and actually getting excess information. So that is the motivation why we factor it and then do it in this form. Because we're only interested in the sign, not the magnitude. And whenever you use the magnitude and the function, so the function is not factored, it's more difficult to do. And you are even not allowed calculators, right? So that's the motivation. That's why we factor, right? So now with this factored form, all that we need to do is what? Is to just pick a number and check the sign for that expression. So within this interval, just as I did here, I'll pick, say, negative 2. Now, negative 2 times 12 is negative. I don't need the magnitude. I don't need the fact that it's negative 24. Maybe if it helps you, that's fine, because that one is easy, straightforward, but we don't need that, right? We just need a sign, right? And when you are multiplying the some numbers, we just need their signs to identify what the end product of the sign will be, right? What I mean is, when you multiply a negative number and a positive number, you know it's negative. When you multiply a negative and a negative number, you know it's positive, right? So the signs are what are needed to identify the sign at the end of the product, right? You don't need a magnitude, right? So that's even more motivation to just do this. So now to pick another, so we are going to use the same number, right? Negative 2. You can change your numbers if you want, but I'll pick the same number, right? Negative 2. So negative 2 here is negative. Negative 2 here is also negative. Negative 2 here is also negative, right? So now negative times negative times negative. The first two negatives will give us a positive, and then a positive times a negative is a negative. Now, because I know the derivative, the first derivative is negative, I know the function is what? Is decreasing on that interval. Please, I hope this makes sense. Okay, so now let's pick another number. I'll do this, and then you guys can please help me with the third one. So now for this number, always pick a number in between, right? Pick a number in between. So between -1 to 0, I have, say, negative half, right? So negative half, a negative half times a 12 is just going to be negative. A negative half minus 2 is also going to be negative. And the negative half plus 1 is a positive number. Negative times positive is positive. So that means the function is what? Is increasing. So the first derivative is positive. So the function is increasing on that interval, right? Can you please help me with the signs for the third line? Give me the first, and then the second, and then the next. And then identify whether it's increasing or decreasing. Can anyone please help me with this? You can unmute yourself and speak, or you can send it in a chat. Either one works. Anybody? Okay, I see something in the chat. So I have positive, negative, positive. Thank you, Taylor. Okay, so Taylor, what will be your conclusion? Do you think the function is, what's the sign of the derivative? And then what is the conclusion? Is the function increasing or decreasing? What will you say? I choose one. Okay, you chose one. Perfect. That's good. And then what's the sign of the derivative? Negative. Perfect. And so because the sign of the derivative is negative, perfect, it's decreasing. Perfect. Thank you. Thank you. That's awesome. Yeah, and you are correct, right? So within this interval, pick a number. I pick one, right? That just as you did. One is convenient. So 12 times 1 is what? Is positive. 1 minus 2 is negative, and 1 plus 1 is a positive. A positive times a negative is negative, and the negative times positive is still negative, right? So with this one, you know that since the f prime is negative, you know the function is what? Is decreasing on that interval. And then the last one, let's do it together. For this one, pick a number, say 3, right? 3 here is positive, 3 there, 3 minus 2 is positive, 3 plus 1 is also positive. Positive, 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 all multiplied together, it's just going to give us a positive. Hence the function is increasing on that interval. Right? Please, are you okay with this? So that's the end of the ID test. Any questions? Now, one advice, whenever you have 0 in the interval, always use 0, because 0 has a very easy way of clearing things up, right? Because a number times 0 is 0, right? 0 divided by a number is also 0, like a non-zero number is also 0. So 0 usually deals with things quickly. So if you see 0 in the interval, it's a good idea to use it. It will help you out to do things quickly. Okay, please, any questions here? Anybody needs time here? So that's the ID test. Right. Okay. If no one needs time, I'm going to the PowerPoint. Okay. So now this is just going to have nice notes of what we did, right? So differentiate factor. And then for the ID test, we know that we are interested in checking for the first derivative, where it's positive, where it's negative. Right? So just proceed to get the critical points. Here, it just moved on to get what? F prime of s equal to 0, right? But please note that for critical points, we check for 2 conditions, where the f prime of s is DNE and where the f prime of x is 0. But for the DNE, we didn't get any cases here. So this one, you are safe. You are safe even if you don't check that condition. And let me write that here so that you note that. Right? But if this thing was going to give us some critical points, then you miss out on that. So it's important you always put it in the back of your head that for critical numbers, you have to check for 2 things, right? Okay, so now with that obtained, we partition the domain of F using the critical points, right? So we get 4 intervals, right? So then we just need to get the sign. So the sign chart, right? So this chart will just show us. So we have the intervals listed here, and then the factors that we got for the F prime, right? We just check for their signs and multiply them together to get the F prime. Then we'll be able to see whether the function is decreasing or increasing there. Please, are you okay on this? Okay. So now the graph of, we are not yet at curve sketching. We get to curve sketching in 4.5, right? But when we get there, we use all of this information. But for now, the graph is already given, right? So as you can see with the graph here, it matches the information that we were able to obtain, right, on this. You see that this point here, I think this point is -1, if I'm right. Yeah, and that's 0. And then where is this? This way, yeah, this somewhere 2, this 2, 1. So you can see that from -infinity, right? From -infinity to -1, the function is what? From the left to the right, right? The function is decreasing, right? And that's the conclusion we made here, right? From -1 to 0, the function is what? Is increasing, as you can see. And that was the conclusion we made here. And then from 0 to 2, right down here, you see the function is what? Is decreasing. And that also confirms this conclusion. And then from the 2 to infinity, the function is increasing. You see, so it matches that, right? Okay. Now, let's move on to local extreme values. This thing has been popping up along the line, but we've not actually looked at how we're going to obtain them, right? So here is where you're going to find local extreme values, right? So for local extreme values, we know that it has to be within a locality. In the locality in math, we are looking at what? An open interval containing that point, right? So either the point is the highest point within that local, right, within that open interval, or is the lowest point within that local, open interval. So now for local extreme values, we are going to use something we call the first derivative test. The first derivative test. So to check for increasing or decreasing, you use the ID test. To try and compute or local extreme values, you use the first derivative test. Now, for the first derivative test, it's not anything new. It just follows after the ID test, right? It just follows after the ID test. But let me explain how, how this makes sense, right? So let's see. Suppose C is a critical number of a continuous function, right? So if C is a critical number, and then you see that the derivative, right, changes from positive to negative at C, then that means that F has a local maximum at C. Let me see the graphs. Yeah, so the graphs are on the next slide. So I'll explain that there. Now the next point B says, if F prime changes from negative to positive at C, then F has a local minimum at C. And then the last point is, if F prime changes from positive to positive, right, at the left and right of C, so it doesn't change, it's just positive derivative here, and after you cross C, it's still positive, then that means that there is no local extreme value there. On the other hand, too, if it changes from negative to negative as you pass through C, then there's also no local extreme values. Now, these points will make sense more when you look at the graphs, right? So for this one, let's look at the first graph, like a 3A. Now for 3A, as you can see, this point C here will be a critical point because at that point, the F prime of the C will be 0. So it will be part of the critical points. Now for this critical point here, C, you see that on the left of the C, the slope of the tangent line is what? It's positive. Now on the right of the C, after you cross C, right, the slope of the tangent line is negative. So this one illustrates the first point here, right? If F prime changes from positive to negative at C, then F has a local maximum. And you can see that with the original curve blue, right, at C, there'll be what? A local maximum there, right? Now for 3B, as you can see, this one too, the C is a critical point, right? It will be part of the critical point list. And then when you look at the left of C, you see that the derivative is what? It's negative. And then to the right of C, the derivative is what? It's positive. So this is the only case where this will happen. So it tells you that the function is taking this form. So that means that there's a what? A local minimum occurring at C, right? Okay. Now the last point, if the derivative to the left of C and then to the right of C are the same, then there's no local extreme values. And with this one, we can see it in two examples, right? For the first part, to the as you can see for C, C will be a critical point because the F prime of C is 0, right? There's a horizontal tangent there, right? But the fact that F prime of C is 0 doesn't mean there's a local extreme value, right? And this illustrates this. As you can see, to the left of C, the slope of the tangent line is what? Is positive. And then to the right of C, the slope of the tangent line is also positive. So it doesn't change. It doesn't change from either positive to negative or positive to negative to positive, right? It stays the same to the left and right of C. Now, if it stays the same, then this is how the graph is behaving, right? Now, as you can see here, at this point C, it's neither greater than or less than any other point in that interval, in an open interval. So it tells us that there's no local extreme value here. On the other hand, if to the left of C and to the right of C, the derivative is negative, then there's also this point here will not be greater than any other point in an open interval containing the C. Neither will it be what? Less than any other point in that open interval. So there's no local extreme value here. Right. Okay. And as I said, this follows directly from the ID test. And we will illustrate this with this example. Please, any questions on the first derivative test? The concept. I'm going to illustrate it here. Okay, so now for this one too, the solution is here. So let's go to the whiteboard. So this is example 3. So for this function, it says find local maximum and minimum values so we have g of x equal to s plus 2 sine of x. And the interval is 0, x, 2 pi. Okay, so let's do this. So solution. Now, for the solution, I'll say, first do the ID test. That's the first thing you do. And then the first derivative test, then do the first derivative test. So it will follow directly, the first derivative test will follow directly from the ID test. Right, so 2 points. So now let's do this. So with the first derivative test, we know that we need the first derivative, right? So we need j prime. So j prime of s in this case will be 1. The derivative of 2 sine x, by the constant multiple, we ignore 2. And the derivative of sine is cosine. So cosine of x. So we have this. Right. Now, after you do this, you factor. But in this case, it's just a binomial. And we can't factor anything here. So we leave it like it is, right? We leave it as it is. Now, the next thing we have to do is what? Is to get a critical points, right? So get a critical points. Now, for critical points, we check for 2 conditions. We check for where this is DNE. In this case, since the expression is continuous, right? It's continuous on this interval. The derivative is also continuous. There's no point, there's no x where the j prime is DNE. So that means that this one is not going to give us no critical point, right? No critical point here. Now, the next condition we have to check is where this is equal to 0. So I do 1 plus 2 cosine of x equal to 0. And then I get cosine of x equal to -1/2. Now, for this one, you have to look at from your Math 127, pre-calc 2, right? You have to get the general solution of this equation. Right, and as a reminder, right? If you have an equation like this, say cosine of some, say theta equal to, say, cosine of alpha, right? If you have this, then your general solution for theta will be equal to what? General solution will be given by 2n pi, then plus or minus alpha. Right, 2n pi and then plus or minus alpha, where n is equal to, so n is in 0, 1, 2, 3, as many as you can in the interval. Right. So this is the general solution, if you recall. The general solution for theta in this case. So now for this problem, right, if you want a general solution for x, then if you have cosine of x equal to -half, I'll need to move on to the next slide, but let me wait for some seconds. If you need more time to let me know. Okay. So now for this one, we have cosine of what? Cosine of x equal to -1/2. So finding the general solution for this, we first get the principal solution, like the first solution. So that will be x equal to cosine inverse of -half. And cosine inverse of -half is I think 2 pi on 3. It's 120, which is 2 pi on 3. Now, after getting this value, you try and plug it in the general solution formula to obtain the other results. So, and don't forget that the interval for this function is what? Is 0 to 2 pi. So all the solutions have to lie between 0 and 2 pi, right? Either 0 to 2 pi inclusive, right? So let's do that. So for the 2 pi on 3, right? Since is this one in that interval? Yeah, this one is in the interval. So that's going to be one of the solutions. But let's look at the general solution. General solution. So we have 2 for the first one. When n is equal to 0, we will have what? Let me erase. When n equal to 0, the solution becomes what? 2 times what? 0 pi plus or minus what? 2 pi on 3. So the solutions are either -2 pi over 3 or 2 pi over 3. But this one is not a solution. It's not in the 0 to 2 pi, so we ignore, right? This one is in there, so we accept it. Now, when n equal to 1, right? So that'll be 2 pi plus or minus 2 pi on 3. So for this one, if you do the plus, we are going to get 2 pi on 3 plus this. That is the same as 8 pi on 3, right? Or the 2 pi on 3 and then this, that's going to be 4 pi on 3, right? Now, once more, this 8 pi on 3 will not be in the interval. So we ignore this and then we accept that 4 pi on 3. Now, if you move on to n equal to 2, the answer that you're going to get is not going to lie in the interval. For n greater than or equal to 2, all the answers will not be in the interval. So the only solutions are 2 pi on 3 and then what? 4 pi on 3. And don't worry too much about trig functions. I'm not going to ask you to do trig, but it would be a good idea to revise them since some of your homework will give you some trig problems, especially I think, is it the mean value? And the 4.1, the absolute maximum or absolute minimum, the closed interval method. There'll be some trig, I think one of them, but I'm not going to test you on trig stuff on an exam, right? So the thing is, we get the critical points. So right, so these are the critical points. Right. So if it's a polynomial, that one is more direct. You get a critical points. That's the goal. Now, after getting the critical points, what do we do? Following the ID test, we partition the domain of the function, right, using the critical points. So in this case, the domain of the original function is from 0 to 2 pi, right? So that's 0 to 2 pi. That's the original thing, right? And we partition using these critical points. So that'll be 2 pi on 3, 4 pi on 3. So that lead to what? 1, 2, 3, 3 intervals. So we then create a table. So we have interval. We have, for this case, right, the J prime is just a binomial. So there's no need to split it up. So we just bring the same thing. So that'll be J prime of X, which is, what's it? 1 plus 2 cosine of X. Right, and then from here we can tell what is happening with J prime, where J of X, whether it's increasing or decreasing. So our first interval is from 0 to 2 pi on 3. So we pick a number and then check. For the next one, we have 2 pi on 3 to 4 pi on 3. And then for the next one, we have 4 pi on 3 to 2 pi. Okay, so for this first interval, you can pick a number. Pick a number that's in this is, because it's 2 pi on 3, I know that pi on 3 will lie in between this. Now, if you check for pi on 3 for this interval, cosine of pi on 3, that's a cosine of pi on 3, that's positive, right? Cosine of pi on 3 is positive. And then 2 times positive is positive. Positive plus positive is positive, right? So we know that the function is what is increasing here. Right. Now, for this interval, you can pick pi, right? The cosine of pi is going to be -1, right? And then that would lead to 1 minus 2, which is negative. Hence, we know the function is decreasing. Now, for this interval, to pick a number, because this is 2 pi, if I want the denominator to be the same, 2 pi is the same as 6 pi on 3. So that means a number that will lie in this interval is 5 pi on 3. Right, so for 5 pi on 3, cosine of 5 pi on 3, that's a positive, and 2 times that is positive, and 1 plus that is positive. So the function is increasing. But don't forget, this is the goal, right? To get to the first derivative, you have to pass through the ID test to get there. But that's not the destination. Please, do you have any questions here? As I said, don't worry too much with the trig stuff, right? Because the trig manipulations, I'm not going to ask you the trig on an exam. So you are free, on the homework, you are free to use your calculators to evaluate some of these things. Okay, now anybody needs time here, any questions? Okay, now we come to the first derivative test, which is on the next slide. So for the first derivative test, this is what you're going to do. This is how it looks like. It's not too complicated, it's just direct. So first derivative test, as I said, it follows from the ID test. So for the first derivative test, just create the partition that you did you use to get the intervals for the ID test, right? So just this partition, recreate it again. So that one is 0. Just bring it here. So you have 0, and then we have 2 pi on 3. We have 4 pi on 3, and we have what? 2 pi, right? So for the first interval, right, just check whether it's increasing or decreasing, right? So you use arrows to indicate that. So something like this. The first one was what was happening there is increasing, decreasing. So increasing, decreasing, increasing. And then you say, okay, now at this point, 2 pi on 3, what you can see here is the function is what? It's increasing. And then as we cross over the 2 pi on 3, it decreases. So the function is behaving like this at 2 pi on 3. Right? So what does that tell us? There's a local what? Is there a minimum or a maximum there? Anybody? What do you think? Is there a minimum or a local maximum there?
Maximum.
Perfect. It's a maximum. Thank you. Right? So here we can say that local maximum value, right, will be equal to what? The function evaluated at what? At that point. And as I said, the dynamics are, for these ones, you have to know the value and where it occurs. So the local maximum occurs here, occurs at 2 pi on 3. But the value is what? The function of what? 2 pi on 3. So local maximum occurs at s equal to 2 pi on 3. Right? Now let's try and get the actual value, right? So g of 2 pi on 3. So for that one, you just plug it in the original g of x, right? So let me look back. G of x is s plus 2 sine of x. So that'll be 2 pi on 3 plus 2 sine of 2 pi on 3. And that one, we can get an approximate value. Let me check. Let me look at the approximate value for that one. So I think that one is approximately 3.38, right? So it's approximately 3.3. Is it 83 or 3? Let me check. Give me a sec. 83. Yeah, it's 83. Okay, it's 83. Right, 3.83. So you have this. So this is your local maximum value, right? And it occurs at what? 2 pi on 3. Now, once again, let's look at this other one. At 4 pi on 3, this is the behavior of the function. It's decreasing to the left of 4 pi on 3, and it increases after 4 pi on 3. So it's like this. So what do you think is occurring there at that point? Is there a local minimum or maximum?
Would that be a minimum?
Yeah, there's a local minimum here. Thank you. Right, so that means that we can conclude and say a local minimum occurs at x equal to 4 pi on 3, and the local minimum value equal to what? The function evaluated at that point, right? So 4 pi on 3. So going back, that means the value is going to become what? It's just going to be 4 pi on j 4 pi on 3. So that would just be 4 pi on 3 plus 2 sine of what? 4 pi on 3. 4 pi on 3. And when you evaluate this with your calculator, you're going to get, let me check the approximate value. I think it's 2 point something. Yeah, it's 2.46. 2.46. So you get 2.46, and that'll be your local minimum value. Please, are you okay on this? Okay, so that's your local minimum value. So that's how you do it. So first go through the ID test, and then you get to the first derivative test. And that's all. Please, any questions? Usually in a typical exam question, right? The one you're going to get on an exam, I'm going to ask you to do everything, right? So you do ID test, you do local, because it follows after ID test. And then you do some other stuff that you're going to talk about. I think I see something in the chat. Oh, the answer. Okay, thanks, Jerry. Yeah, so that's it on this. Anybody needs time here? Okay, then let me share the screen. So this is just going to give us a solution, right? Some nice notes to follow. So, and it's going to give us a graph to show us that there's local extreme value, right? So there's a graph. So as you can see, the graph is from 0 to 2 pi. And then within this, you see this point here. That's what? A local maximum, right? It occurs at 2 pi on 3. And then the maximum value is the function evaluated at 2 pi on 3. And then for 4 pi on 3, that's a local minimum occurring there, right? And then the value is what? G of what? 4 pi on 3. I think it's time. It's 11:50. So the next time we meet on Monday, we're going to talk about what f prime say about the function f, right? So thank you for your time today. If you have any questions or you want to work some more examples, feel free to reach out to me, right? Okay, so that's all. And then have a nice weekend.
Thank you.
You are welcome.